All right. I welcome you guys to this wonderful lesson. And we are going to be looking at differential equations. A series of them have been recorded and yet to be posted. Yeah, so let's begin with this first lesson, differential equations, or what we may call DEs. Differential equations or DEs. Now, when we say a differential equation, this is an equation which involves the differential coefficients, call them derived functions, like dy dx, the 2y dx squared, the 3y dx cube, up to the ny dxn. Yeah. So without wasting time, I need to first let you know that for you to cover this topic, you need to be very well versed with the integration and somehow versed with the differentiation. For we are going to be applying those two ideas to calculate numbers this side. Under the topic of differential equations, as we are going to be meeting in front there, we shall look at even the applications of differential equations, whereby we are going to see that differential equations is a branch of mathematics that has got very, very many applications. Yeah, to begin with, let's begin with the order of a differential equation. Order of a differential equation. So when we say the order of a differential equation, we are meaning that you order any, the value of any, yeah, of the highest derivative. Order n of the highest derivative that is contained in the differential equation, the highest order. Yeah, the order n of the highest derivative. For example, if you look at this equation, for example, if you look at like this one, dy dx plus y is equal to 4. This is a differential equation with the derived functions or with the derivatives dy dx, but we don't have any other derivative. Derivative there must begin dy dx, 2y dx square, etc. So if we have dy dx plus y is 4, it means that this one, the order n of the highest derivative is still this, dy dx. So we say that this is a first order differential equation. Yeah. So this is first order differential equation. Yeah. So if we have an equation like the 2y dx square plus 2 dy dx plus 5 is 0, look for the highest derivative. The highest derivative is that one with the n, where the n is big. Yeah. So if you look at these two, we have the 2y dx square, that is the first derivative. We also have dy dx, that is another derivative. But the highest derivative is this, and the value of n is 2. Therefore, we say that this is the second order differential equation. If I write an equation like dy dx plus 5d3y dx cubed is equal to 4. Looking at this, it has got two derivatives where we have dy dx, we have the 3y dx cube. But from mere observation, we see the highest derivative is this. Therefore, our order of this differential equation is 3. So this is the third order differential equation. Third order differential equation. So in today's lesson, we are going to be interested in types of solutions, how to form a differential equations basically for today. Then in our next lesson, we shall be looking at solving first order, second order equations. So our other subheading is solution to differential equation. When we say solution to differential equation, this one here involves the elimination of all differential coefficients. Yeah, all the differential coefficients you're given, the moment you have eliminated them, we say that what you've got is what we call a solution to the differential equation. And that solution to the differential equation is normally done by integration. Yeah, so this one involves the elimination of all differential coefficients. Of all differential differential coefficients in a DE. So it's done by integration. For example, let's have some examples. Just very fast examples. I can say solve the differential equations. So the differential equations. A, we are having dy dx minus 5 is 0. And B, we are having dy dx plus 10 is equals to 0. Yeah, now having this, since we are just introducing, we are still under the introduction. The better the introduction, the better your understanding. So to begin with, if they say that we solve this, it means we have to eliminate this dy dx. We have to eliminate dy dx in both cases, because we said that the solution, when you solve, you get a solution, of course. So the solution is the elimination of all differential coefficients done by integration. So like for part A, if you look at dy dx minus 5 is 0, this is the same as dy dx is equals to 5. If you bring a 5 this side, implying that our dy is equals to 5 dx. You cross multiply, right? So if you do integrate both sides, you integrate dy, you integrate 5 dx. So when you integrate both sides, when you integrate dy, you get y is equal to, when you integrate 5 dx, you get 5x plus a constant of integration. What you have obtained is what we call a solution to this differential equation. The same applies to part B. If you're having dy by dx plus a 10 is equal to 0, yeah, so here we shall have dy is equal to negative 10, yeah. I'm writing very many donkey steps, but otherwise one can say dy is equal to negative 10 dx. Yeah, dy is equals to negative 10 dx. If we integrate both sides, we integrate dy, you get y. We integrate negative 10, you get negative 10x plus a constant of integration. What you've gotten is what we call a solution to the differential equation given. But these solutions have got different types. We have what we call a general solution and a particular solution. So let's now go to a section that tells us the types of solutions of a differential equation. Types of solutions of differential equations. Now, the type of solutions, they are just two. The first one is called a general solution. First one is called a general solution. And this general solution is the one that contains an arbitrary constant of integration. Yeah, contains an arbitrary constant of integration. Yeah. Meaning that the moment you finish integrating and you say plus C, that is what we call a general solution. So the solutions obtained in the other examples which I've just done are called general solutions, where there must be a constant of integration after integrating. Then the second type of solution is what we call a particular solution. Now, a particular solution is where we eliminate that constant of integration. Yeah. So when we have to eliminate, general has a constant of integration, but in particular, we eliminate that constant of integration, right? So here we eliminate the arbitrary constant, and it's normally done by use of initial conditions, right? So when I say initial conditions, let me first show you that here we eliminate using initial conditions. Yeah, so in this case, you're given, if it is y and x, you're given the values of y and x, you substitute them so that you eliminate a constant, or you substitute for the constant. Without wasting any time, let's have a look at two examples that look or that bring out the meaning of these two terms. So let's have two examples about that. Examples. Solve the differential equations. One, we have y dy is equal to x squared dx. Two, we have y dy is equal to x dx, given that y is equal to 1 when x is equal to 0. The moment they say given that, and they give you these values, these are what we call the initial conditions, meaning that by using this, we are no longer going to obtain a general solution, but instead a particular solution, because you have what to substitute and get the final answer. So to look for the solution very fast, for part A, we are having y dy is equals to x squared dx. Now, if you're given this, it is already separated for you, so just integrate, right? So we shall integrate y dy is equal to integrate x squared dx. When you integrate y dy, we're going to get y squared over 2. You increase the power by 1, you divide by the new power. So we shall have y squared out of 2 is equal to, when you integrate here, you increase the power by 1 and divide by the new power, it will be x cubed out of 3 plus a constant of integration. So what we've gotten here is what we call a general solution. In an exam, you do not need to write in brackets that it's a general solution, yeah, because I will easily see that since no initial conditions are given, what you obtain at the long last is a general solution. Part B, we are having y dy is equals to x dx with the initial values given. So what we do here, we shall integrate both sides immediately. Y dy is equal to the integral x dx. When you integrate y, you get y squared out of 2 is equal to, when you integrate x, you get x squared over 2, of course, plus a constant of integration. But they want you to substitute in for when y is 1, and when x is 0. That one will eliminate the value of constant c, then we introduce it here. So what we do, you will say that for y is 1 and x is equal to 0, substitute there. It means that we shall have a half 1 squared. A half is equal to 0 over 2 plus a constant, meaning that our value of c is equals to a half. That a half, you substitute it here so that you eliminate constant c. So to eliminate constant c, it's when you have substituted for the value of c, implying that our y squared out of 2 is going to be equal to x squared out of 2 plus a half. By multiplying a half throughout in order to make it seem to be in terms of y, we shall have, if you multiply by 2 throughout, you're going to have y squared is equal to x squared plus 1. And this is what we call a particular. It is having a particular variables, and that is x and y. So this is what we call a particular or a particular equation. A particular for its solution. So that is, those are the two types of differential solutions that I can define for you. And that one is taking us very fast to the formation of differential equations. How do you form these differential equations? So my heading is forming differential equations. I will use the word is throughout my lessons. So forming differential equations. Now, it means that here we are going to form that equations with differential coefficients by eliminating arbitrary constants. So in this case, we eliminate arbitrary constants and come up with the equations with differential coefficients. So in other words, now they give you an equation like the final equations we've been getting as solutions. Then they tell you to form a differential equations with the coefficients like the y dx, something like that. Now, if the equation has got one constant of integration, then the differential equation formed will be first order. If you have only one constant of integration, we are going to look at examples. If you have only one constant of integration, you form a first order, meaning that the highest derivative has order 1, dy dx, something like that, d theta d, dt d theta, ds dt. It must be having the highest value of n as 1. Yeah. On the other hand, if it has got two constants of integration, then the differential equation formed will be that of second order, whereby the highest value of n in the differential coefficient must be 2. Let's look at examples. From differential equations from the following. Roman 1, y is equal to x plus a out of x. Roman 2, y is equals to a cos theta. Roman 3, y is equals to a x squared plus bx. And Roman 4, y is, okay, let me say x is equal to tan ay. By me doing for you this, I'm going to give you an exercise which you can practice and see the answers you are going to get. So part of the solution, Roman 1, we are having y is equals to x plus a out of x. This one should tell you that the answer you'll get will be first order because you have only one constant of integration. Other variables are common, y and x. So what we do, first multiply x throughout so that you make the constant, let the constant be separate. Yeah. So it means that if you multiply by x, by x, by x here, we shall have yx is equal to x squared actually, plus a. I've multiplied by x either sides. Now, it means that my a will be equaling to yx minus x squared. And I can easily factorize out the value of x. So my a is going to be equal to x, y minus x. I'm having that. So I can differentiate both sides. Yeah. Yes, I can get the dy dx. So my dy dx is equal to 1 minus a over x squared. So implying that you have, if I substitute for the value of a here, in what I've done, I've just made a constant the subject, and I've gotten this. Then I come back to my equation, I differentiate it, dy dx. When you differentiate dy dx, here it will be dy dx is equal to, when you differentiate with respect to x, you get 1, while this one, a over x, if you differentiate a over x, this is the same as ax power negative 1. So you drop negative 1, then a x, you reduce the power by 1 to become negative 2, which will be negative a out of x squared, which is this. So now, after I substitute, because in a differential equation, there is no constants. There is not supposed to be any constant. So you have to substitute for this value of a into this equation. So what we shall have will be, let me say that this is my equation 1. So substitute equation star into equation 1, or you substitute for the constant. It means that we shall have dy dx is equal to 1 minus the value of a, but the value of a is x into y minus x, yeah, then over x squared. So this is the same as 1 minus, because this is yx, so it will be y minus x over x. Because this is the same as, when you open the brackets, this is the same as xy minus x squared over x squared. Yeah, it's the same as xy minus x squared over x squared. So you can divide through. Yeah, so when you divide through, you're going to get this one cancel with this. Or we can divide by x only, because here we don't have a square. So it is x with x squared will remain x, and here will remain x also. So this is what we are having. So now what you do, we have dy dx is equal to this. So we can multiply by x throughout. So it will be x dy dx is equal to which is equal to, here of course the LCM is x, and it's what I multiply here. So it's going to be x minus y minus x. minus negative x. This is supposed to be plus. This is minus xy plus. It's supposed to be a plus. So I will have x dy dx is equal to x plus x, that is 2x, then minus y, which is the first order differential equation. So from there, let me do you some other example 2, where we have y is equals to a cos theta. Y is equals to a cos theta. Because we want to eliminate this, we need to make it the subject. So my a will be equaling to y over cos theta. So when you differentiate this, the dy d theta, now I call this one my equation star maybe, then I differentiate my original expression. So when you differentiate it, you're going to get dy with respect to theta is equal to, when you differentiate a cos, you get negative sign, so it will be negative a sine theta. So if you have dy d theta as that, now what is remaining is just substitute for the value of a. So substitute equation star into equation 1. So when you substitute it, you are going to get dy d theta is equal to negative a, so it will be negative y over cos theta, then sine theta. So we are going to have dy d theta. So this is sine over cos, which will be tan. So it will be negative y tan theta. A student can stop it here, or the student can say dy d theta plus y tan theta is equal to 0. Still, this is first order differential equation. Yeah, that is first order differential equation. So you see, because we had one constant, our answer is in first order. Then second last question, which is our number 4. Our number 4 is, we are having y, actually our number 3, y is ax squared plus bx. Yeah, so we need to first get these constants. We need to first get what a is equal to and what b is equal to. So if I call this on my first equation, if it's a second order, you have to be very smart. So I can first differentiate this dy dx. Why am I saying dy dx? Because I have variables y and x. If you have y and theta, you differentiate dy d theta. So it is going to be 2ax plus b. I call this one my equation 2. Yeah. Because I have two constants, I know that I may get an answer with the second order. So I can look for the second derivative, the 2y dx squared. When you differentiate for the second time, this is going to give you 2a. So from this, I can call this one my equation 3. Now it means that from equation 3, I can get the constant a. So a is equal to, I divide by 2 both sides, so it will be a half of the 2y dx squared. Yeah. Now, if I substitute the value of a into equation 2, I will get the value of b. So substitute A into equation 2. So I'm going to have dy dx is equal to 2 times A, which is a half, the 2y dx squared then times x, then plus b. So dy dx is equal to, this one will cancel, so I will have x to 2y dx squared plus b. So this one will give me the value of b, and the value of b which I will get will be b is equal to dy dx, yeah, then I subtract x the 2y dx squared. My interest is to substitute the value of a and b in this equation, and I eliminate those constants. So substitute a and b into equation 1. So when we substitute a and b into equation 1, it means that we shall have our y is equal to ax squared. Our value of a is a half x squared, because I'm substituting the value of a. So then the 2y dx squared plus bx. Dx, it means I'll have x multiplied into the value of b, which is dy dx minus x, the 2y dx squared. So it means that our y is going to be equal to a half x squared, the 2y dx squared plus x dy dx minus minus x squared, the 2y dx squared. Yeah, implying that all this equation, I can say because I have a half x squared minus x squared. Yeah, a half x squared the 2y dx squared, x squared the 2y dx squared. So when you get a half minus 1, you get negative, right? So allow me say that this is the same as this and this will form negative a half, because I'm getting a half x squared, I'm subtracting x squared, so it will form negative a half x squared. So if I bring it this side, it will be a half x squared, the 2y dx squared. Then if I bring this on this side, it will be minus x dy dx, then they have found y, so plus y is equal to 0, which is a second order because the highest derivative has got n as 2. So this is my second order differential equation. Then finally, I am having number 4, where we are having our x is equals to a tan y tan ay, sorry. So we are going to differentiate with respect to x. So dy dx is this side. Let me call this one equation 1, where I will substitute the value of a. I'm interested in getting the value of a. So allow me say that 1, I'm differentiating. So with respect to x, you get 1 is equal to, when you differentiate this, you first bring a constant this side, a. When you differentiate tan y, you'll get sec squared. Of course, when it is, allow me remind you from this, if it is sine 2a being differentiated, first bring a constant, which is 2, then you differentiate sine, which is cos, then you put 2a. So the same applies. I've dropped a constant a, then I differentiate tan, which would be sec squared, a y, but because it is not in terms of x, I'll just say dy dx. I'll just say dy dx, implying that 1 is equal to a sec square x is the sec square ay is the same as 1 plus tan square ay. Then of course dy dx. Now we can substitute for tan ay so that we move away this. So substitute for tan ay, it means that we shall have 1 is equal to a into 1 plus tan square ay will be, tan ay is x, meaning tan square ay will be x squared, then dy dx, right? This one can give us the value of a. So the value of a would be the same as 1 over 1 plus x squared dx dy. I'm dividing the whole of this, both sides. So the x will move up, dy will move down on a division. So this is what I am having. Now I'm going to substitute for the value of a, substitute equation 2 into equation 1. Substitute equation 2 into equation 1. It means that we shall have our x is equals to tan, then ay, right? Tan ay. So a is 1 over 1 plus x squared dx dy, right? Dx dy, then times y. So which is the same as x is equal to tan, y can come here, can have y over 1 plus x squared, yeah? Then dx dy. So this is x is tan this, meaning that tan inverse of x, if we bring tan either sides, yeah, it's like when I say x is equals to tan theta. So what is the theta? Theta is tan inverse of x. So here, this is like my theta, all of this. So my theta, which is y over 1 plus x squared, yeah, dy dx is equals to tan inverse of x, implying that actually it is dx dy, implying that dy dx, or if we multiply, if we make y the subject, yeah, it is going to be y is equal to, this one will come here, so it will be 1 plus x squared tan inverse of x, then dy dx now. So this is first order differential equation. So you go through again, you're going to see it very direct. You're going to see it coming out very direct. I'm giving you exercise. From differential equations from each of the following equations. Y is 3x squared plus ax. Y is a over x. Number 2a, y is 4x squared minus a. While b, y is ae x squared. Number 3a is y is equals to a ln x, while b is y is equals to a cos x. Number 4 is part a, x squared plus 4y squared is a, while part b is y cubed is a, x squared plus 1. 5 is y squared is equals to xy plus a. That is our first lesson. And we are going to load the second lesson. Nice time, and tomorrow we are starting from first order differential equation. The video is reaching you very soon.